Hello, I'm Ewan Crawford, and together with my colleague Jack Frankland, today we'll be talking to you about the command buffer extension released by the OpenCL working group at the end of last year, and our experience implementing it. So a bit of background on us. We work for CodePlay, a company based in Edinburgh, Scotland, and our goal is to make AI and HPC open and safe to everyone by contributing to open standards and participating in open source projects. The company designs and implements programming models, compilers, and tools for multiple vendors. Of particular relevance to this talk, myself and Jack work on our Computer product, which implements OpenCL. And that's the basis of our collaboration with the OpenCL working group on the command buffer project. So what we're going to talk to you about today, I'm going to give you some background as to why command buffer extension came about, go over the API itself, and then cover some design decisions we took while coming up with it. Then hand over to Jack, who's going to talk about our experience implementing it in Computer and some next steps. So I'm not going to give too much background in OpenCL here. Suffice to say that OpenCL allows a programmer to offload a sequence of commands to a heterogeneous accelerator. And we found that there's a cost of creating these commands, in particular from embedded devices. And when an application has a repetitive sequence of commands, we find that we're paying that command construction cost every time we're enqueuing that sequence, which is redundant. Another side effect of constantly having to create commands is that it introduces latency to enqueuing work on the device. So ideally, we'd like our accelerator device to be occupied with work. But by having to wait before you can enqueue your commands to it, that increases the latency and reduces its occupancy. And we've found that this impacts performance in applications where the same command sequence is used to process different inputs, in particular computer vision applications operating on images. So how do these problems manifest themselves in the OpenCL API at the minute? Starts with the design of CL and Q command entry points, which both create a command and schedule the command for execution. What we'd like to do is separate these concerns. So we have a distinct API for controlling command construction and a separate API for scheduling those constructed commands for execution. That means you just pay the command construction cost once, and we can have a low overhead command submit entry point for keeping devices occupied with work. And this is a proven abstraction. Vulkan has VK command buffer, Intel has Intel level 0 command list, and CUDA has CUDA graphs. So this is very much a device agnostic solution that should work across a range of domains. So here we've got a motivating example, which we'll refer back to throughout the talk. And it's a snippet of code taken from an image processing application we have that operates in tiled memory, doing some sort of image processing task inside the kernel. I think it was Grayscale. So talk through it quickly. We've got 4 buffers, a frame input, and tile input and tile output. Then we kind of do some program setup and iterate over all our frames. For each frame, we copy that data for that frame into the frame input buffer. And for however many tiles we want to operate on, we iterate over them, copying that data to a tile buffer that the kernel will process. And then once we've iterated over all our tiles, we'll read that data back from the frame output buffer. And really what I want to highlight here is that there's a repeated sequence of commands in this inner num-tiles loop that we have to do for every frame. So the command buffer extension. This OpenCL extension was made public by the OpenCL working group in November 2021 as a professional extension. And this was created from the contributions by many OpenCL working group members, not just CodePlay. And this really formalizes this separation of concerns solution. And you can find the extension specification in the registry at the URL at the bottom of the slide. So to talk through quickly the life of a command buffer, first of all, create a command buffer targeting a particular device. User then records commands to a command buffer using some new entry points we've defined. Then finalize the command buffer, which ends the recording and no more commands can be added. And finally, the user can submit that command buffer 1 or more times asynchronously. And we've also got some device queries available in the API that lets the user see what particular optional functionality our implementation supports, and also any queue requirements that might restrict how you can use a command buffer. To come back to our example again, we've rewritten it this time to make use of the command buffer extension. And I'll talk through some of those APIs to illustrate them. Essentially what I've done here is lifted the inner numtiles loop into command recording. The first thing we need to do before we can record this command is create a command buffer, and that returns a new type we've defined. And on creation, we pass a list of queues that a command buffer can be created with, and this is a queue. These are the queues that a command buffer can record commands to. For the extension, you can actually only pass a single queue for the moment, although it's possible in the future you could allow more queues to be passed, and I'll talk about this later on in the talk. After we've created our command buffer, we then record commands to it. So the API I've picked out here is the CL command ND range kernel KHR entry point. And this is the equivalent of CL and Q ND range kernel in the core API spec. And it starts with a command buffer to record the command to in a particular queue that represents the device you'd like to record the command for, and all the command recording entry points start with these two parameters. And actually, because we're only using a single queue at the moment when we create the command buffer, the second parameter can be null, so we already have that information. There's then some properties, and then all the standard parameters to CL and Q ND range kernel are used up until we get to events. And instead of OpenCL events, we've instead got an equivalent called sync points that can be only used for synchronization inside the command buffer. And more about why that is later. And then finally, the last parameter is a mutable handle parameter, and that essentially provides a handle to this command in the command buffer that we can use to reference it later on in the application. And again, I'll talk about why there's extra functionality permitted, but not defined immediately later on. Then end the recording. We've got all our commands with the CL finalize command buffer entry point. And because at this point, the runtime knows the exact structure of the command buffer and all the dependencies, it can potentially perform some optimizations. But having an explicit entry point gives the user kind of control over when to incur that latency of any optimizations here, rather than having to pay it when you enqueue the command buffer. Finally, each frame being a kind of enqueuer command buffer. And this takes a list of queues to enqueue the command buffer to. So this will actually be a single queue, because right now we only support a single queue. But it doesn't have to be the exact same queue that was used on command buffer creation. It can be an equivalent queue, as be compatible, which means the same device, same properties, same context. And that takes a list of events, so we can synchronize this command buffer enqueue with regular OpenCL commands. So that's a talk through of the extension itself. I'm now going to discuss some of the decisions we made in the OpenCL working group when we were coming up with this extension, kind of starting very far back at the beginning when there was a few different approaches discussed for creating a command buffer or recording a queue. So what in our proposal released here, we've got new entry points for recording commands, but because these are essentially equivalents of the core OpenCL spec, another approach was to just use the existing entry points and have some sort of recording state to capture them. So I've kind of created a hybrid proposal from those earlier discussions here to illustrate that in the pseudocode. Essentially, what we've got here is we put the queue into recording state where we can record the regular commands between begin and end recording. And the advantage of this is that it's much easier for users to update their application to use this extension as there's fewer new entry points to use. There is overall, though, quite a few different pros and cons with this stateful design. One aspect is maintainability of the extension. So right now, if we add a new entry point to the OpenCL spec and we want to include it in the command buffer extension, right now we need to release a new iteration of the command buffer extension, possibly a layered extension to support that by adding in a new command. However, in a stateful design, it can't automatically be included between the begin and end recording entry points. There's a flip side to this though. If it's this new entry point that's added to the OpenCL spec we don't want to include, we can currently just ignore it, which is zero cost and it's not included. But with the stateful design, we need to add wording to the spec to forbid it. And on the side to it is the user usability. So having the smaller, and this is, I guess, of code rather than the spec, so having the smaller API footprint and less duplication of entry points makes it easier to use in existing applications to support. However, it might be harder for users to reason about code that's stateful because they have to keep a mental note of what that is. So if we just go back to the previous slide, in this num tiles loop, if we imagine that is abstracted out into a different file that doesn't have the beginning and end queue recording entry points in it, it would be hard for someone reading that code in isolation to know that actually work isn't being queued to the device at that time. Some of the aspects of how introducing new entry points, one of them is it allows us to constrain the scope of what we allow to be used with command buffers. So for code plays case in particular, we wanted to restrict access with host. So for that reason, we can push for no read, write, map buffer commands in the absence of CL event, which would allow host callbacks and host synchronization. And instead, introduce this command buffer only synchronization point. However, in the stateful design, if we wanted to do this, we'd have to add a lot of checking for CL event usage and banning it, which would increase possibly the minimum bar to implementing the extension and add a lot of additions to the spec itself, which might make it more difficult to read. However, for any vendors in the future that do want this functionality of being able to synchronize commands outside of a command buffer, it would be a bit easier to enable that, as they just need to restrict, loosen that wording. And finally, control. I think this is probably the most valuable case for new entry points, and that's it can add new parameters to our new entry points when we define them. So, in particular, the mutable handle parameter we've added that allows the user to have a handle to a particular command in the command buffer. Otherwise, if the user wanted to reference a particular command, they might have to remember exact indices of that command in the command buffer, which is a lot of bookkeeping for a user to have to perform. Whereas for the new entry point design, we can just add a handle to use. I'm now going to discuss the comparison with Vulkan command buffers. So Vulkan is other Kronos standards that has the command buffer abstraction, and it distinguishes between primary and secondary command buffers. Primary command buffers are submitted to queues, while secondary command buffers can only be executed from another command buffer. And OpenCL command buffers are all primary command buffers. So this is because this is the main drive from implementers when we're looking for this. I think there is possibly a case for secondary command buffers if we want to represent some sort of graph, and you had a particular node which was a graph in itself, so a subgraph, and that might be nicely represented by a secondary command buffer. However, this is just speculation, and there is no immediate drive from vendors to implement something like this, so it's omitted for the moment. Similarly, for VK reset command buffer, there's no equivalent OpenCL entry points, but we could discover that if the creation destruction pattern is prohibitive to performance, we could possibly add that in later on as an additive change. A comparison with some of the properties that a Vulkan command buffer can be created with. The one-time submit bit and the render pass continue bit don't have equivalents. However, in OpenCL, we do have an equivalent of the simultaneous use bit. And this indicates that a command buffer can be submitted while another submission of the same command buffer is already in flight. And this is optionally supported by devices, so you don't have to support it, but we do in Compute-Orta, and Jack will talk about implementing it later on in the talk. So the final thing I'm going to discuss with you is the idea of layering. So the command buffer abstraction unlocks a lot of possibilities in terms of functionality, which initially when we were designing the spec made it manifested as lots of optional capabilities. And we found that it was getting quite unwieldy to kind of use a spec. Implementing all the optional features would take a long time, and that means a long time to release it publicly, and implementations and CTS and all these things. So instead we decided to layer the extensions. So the command buffer extension is the base level extension, which reduces the kind of minimum amount of functionality needed to support it by vendors, which will hopefully improve uptake, and it's also a bit more readable for users when you're reading the document. However, some of those layered pieces of functionality I can talk about cover at the minute, and we're hopefully going to be able to say more about them this year. One of the first ones I'm going to discuss is the mutable kernel command extension. So this makes use of that mutable handle return parameter from command recording entry points. And what it does, it returns the particular handle to a command in the command buffer. And this allows you to, between enqueues of the command buffer, modify that command in particular, if you want to. So we found that if you've got a very slight change to a kernel command, like maybe the ND range configuration or the arguments, in the case of double buffering, then it's very handy to change this between enqueues rather than having to record a whole new command buffer, which could have a lot of commands, only to change slightly one kernel command. The other layered extension we're looking at is the multi-device command buffer extension. And the idea of this is we can use that full list of queues rather than restricting just a single queue. You can create a command buffer with multiple queues and then specify on the command recording exactly which queue you want to record to, which could be to different devices. So that covers what I'm going to say in this talk, and I'll hand over to Jack to talk a bit about our implementation experience. Over to you, Jack.
Thank you, Ian. So as we mentioned in the introduction, we're going to briefly run through our experience of implementing the OpenCL command buffer extension and draw your attention to a few bugs we hit along the way, with the hope that any vendors going away from this talk who want to implement this extension for themselves can bear those in mind. So I'll begin by very quickly talking about Compute Aorta, which is CodePlay's toolkit for building heterogeneous compute runtimes. And amongst a lot of other things, Compute Aorta consists of an OpenCL implementation, which is layered on top of ComputeMux, which is CodePlay's proprietary API, and we'll talk about that a little bit more in a second. We haven't got time to do a deep dive into Compute Aorta today, but for those that are interested, there's a really great IWOCL talk from 2020 by my colleagues Alistair and Ewan, where they do a deep dive into Compute Aorta, all of the components and libraries that make it up, and the design philosophy behind the Compute Aorta project. So I recommend that if you're interested. But for the purposes of today's talk, we can kind of just think of Compute Aorta as an OpenCL implementation layered on top of ComputeMux. So ComputeMux is CodePlay's bare metal compute API. And the idea behind this is that it's a fully spec'd API, and hardware vendors can implement ComputeMux for their device in order to enable open compute standards on their platform. So as I mentioned, in Compute Aorta, we have an OpenCL implementation layered on top of ComputeMux, but we also have a Vulkan implementation that's layered on top of ComputeMux. So by writing a ComputeMux implementation, you can enable those open standards. And the reason we're talking about ComputeMux today is that ComputeMux actually already has a concept of a command buffer, and we call these MUX command buffers. And these existed before the OpenCL command buffer extension. And we, in fact, already use these in OpenCL to implement regular OpenCL commands that are enqueued to a command queue. And we'll talk a little bit about that more. We'll talk a bit more about that later. But the point I want to make here is that we use these MUX command buffer objects to implement the OpenCL command buffer extension. So the CL command buffer KHR objects that we saw earlier, in our implementation, are wrappers over MUX command buffers. And there's lots of associated machinery that does things like creates the OpenCL command buffer, retains it, releases it, destroys it, does all the reference counting, enqueues commands to the command buffer, finalizes it, all that type of stuff. So yeah, an important point here is that in our OpenCL implementation of command buffers, the OpenCL command buffer object is a wrapper over MUX command buffer. And for the rest of this talk, I'm going to try and make it very clear when I'm talking about MUX command buffers and OpenCL command buffers, because there's a difference there. So finally, on the slide, a little aside is that our MUX command buffers are currently defined to be in order by the MUX spec, which means that our OpenCL command buffers are, for the time being, in order. So I mentioned there that we were using MUX command buffers to implement regular OpenCL commands. And in the red box on this slide, I've got some of the more common enqueue APIs in OpenCL for enqueuing commands to a CL command queue. And then in the blue box, I've got some of the MUX APIs that add MUX commands to command buffers. And under the hood in our OpenCL implementation, this is how we implement these OpenCL APIs. So you can see the mapping is one-to-one. And for each command API in OpenCL, there's a corresponding one in Compute MUX. So when it, sorry, slide there. So when it came to implementing the OpenCL command buffer extension, we already had all of the MUX APIs we needed to actually add commands to command buffers. And on this slide in the red box, I've now got the new APIs from the OpenCL command buffer spec. And in the blue box, I've got those same MUX commands that we use internally in our OpenCL implementation. There are, of course, also MUX commands for creating command buffers, MUX command buffers, destroying them, finalizing them, which I haven't shown here since the mapping is less one-to-one. But the point I'm making here is that we already had all of the machinery we needed in MUX to implement these entry points. So with that very high level overview of how we implemented the OpenCL command buffer extension and how we also implement the regular enqueue commands in OpenCL, I'm going to talk about the first bug that we ran into, which is to do with command batching. So the reason we're using MUX command buffers to implement regular OpenCL commands is actually to try and solve one of the issues that Ewan mentioned at the start of today's presentation, which is to do with the fact that on an embedded device, the cost of building a command list or a command stream can be quite expensive. And because in OpenCL, there's no way, as Ewan said, to decouple enqueuing a command from executing it, what we do internally in our CL command queue implementation is we actually batch commands together. So when a regular OpenCL command is enqueued to a command queue, that command is batched into a MUX command buffer according to certain constraints. And we term these command buffers pending dispatches, since they're groups of commands that haven't actually been dispatched to the device yet. And these pending dispatches actually only get sent to the device when there's a blocking event or a flush in OpenCL. And so the idea here is that rather than incurring the cost of building a command stream for every command that's enqueued to the command queue, you just incur it once when there's actually a flush to the device. So instead of incurring the cost of building n command streams for n commands, you incur it once for n commands. I should point out here that this doesn't solve the problem of reusing groups of commands. Since this is internal to our command queue, there's no handle on this pending dispatch for the user, which means that once it's been dispatched to the device, it's lost. And if you want to enqueue the same group of commands again, you have to rebuild that command stream. So this solves one of the issues command buffers aim to address, but not all of them. So I mentioned there that there's some constraints on what commands can be batched together. And this essentially comprises our batching algorithm, which is as follows. So when you enqueue a command to a command queue, if that command has one or more wait events associated with commands in a single pending dispatch, so that command is waiting on commands to execute that have all gone into one command buffer, then you're free to just push that command into that command buffer. And I should say here that because Compute AOTA currently only supports in-order queues, there's always an implicit dependency on the last command that got enqueued. So if you are pushing your command into a pending dispatch, it's always going to be the last pending dispatch that was added to the list of pending dispatches. The second case is that you have two or more wait events associated with commands in different pending dispatches. So this is the case that your command needs to wait on commands that are in separate pending dispatches. And in this case, all we do is we get a new unused command buffer and we stick our command in that command buffer. And then the third case is there are no wait events, which means that there's nothing in the queue, or there are wait events with no associated pending dispatches, meaning that your command needs to wait on other commands that are already being executed or have already executed. So under this scheme, the command queue is responsible for creating MUX command buffers, destroying MUX command buffers. It can reset them since they can be cached and reused, and we do that via this MUX API. And then we won't talk about this too much today, but the command queue is also responsible for creating, destroying, caching and signaling MUX semaphore objects, which are used to express dependencies between command buffers. And the command queue is also responsible for signaling and waiting on OpenCL events. So I said that the batching of regular commands presented a problem when we were implementing the OpenCL command buffer extension. And I'm going to run through an example here, and hopefully we'll see why that's the case. So on the slide here, this code snippet is from Ewan's example earlier, and this is the code that actually builds the command buffer. So in this example, we enqueue a copy, we enqueue an ND-range kernel, and then we enqueue another copy, and we do that in a loop for a number of tiles. And in the green box here, I've tried to give a visual representation of what this might look like. So these blue boxes represent the commands inside a command buffer. And then on this slide, I've got the code that actually enqueues the command buffer to the command queue. And in this yellow box, we're going to see the list of pending dispatches that get created as we enqueue those commands to the command queue. So I'll walk through this, this example, and hopefully we'll see what goes wrong. So the first thing that happens is we enqueue our write, and this isn't waiting on any commands. So according to that batching algorithm, we're free to take a new command buffer and put our command in that command buffer. And that forms our first pending dispatch. So you can see now that we've got this write, and it's gone into its own command buffer. The next thing we do is we enqueue our OpenCL command buffer. And here we do the obvious thing. We take the MUX command buffer that OpenCL command buffer wraps, and we just stick that in our list of pending dispatches. So now you can see in our list of pending dispatches, we have our command buffer from the previous slide. And I should pause here just to point out that I've removed the loops from this example, just to simplify it a little bit, since it's not relevant to see what goes wrong. And then we enqueue our read. And this is where, things start to go wrong. Because what happens when we enqueue this read is that since we're in an in-order queue and we only have a dependency on the last command that got enqueued, the batching algorithm says, hey, well, I've only got dependency on the last command, which in this case is the OpenCL command buffer being enqueued. So I can get the underlying pending dispatch from the last command, and I can push this read into that pending dispatch, which is what happens. Now the read's gone into the previous pending dispatch. But the problem in this case is that this pending dispatch is a MUX command buffer that's underlying an OpenCL command buffer object. So this is something the user created and added commands to. So we've actually changed here the behavior of the user's command buffer. And this might not be a problem in this example, since in this loop, the commands are still all going to execute in the same order that they otherwise would. But you could imagine the user takes their command buffer and uses it somewhere else in their application, and all of a sudden they've got this read that they didn't add. So this obviously isn't the desired behavior, since we've changed the semantics of the command buffer. But what's even worse is that in our testing, we are seeing examples of the command buffer appearing in a corrupt or invalid state. And this was because, as I mentioned earlier, the command queue is free to destroy or reset command buffers after they've finished executing. So we're finding cases where the underlying MUX command buffer in an OpenCL command buffer object have been freed or destroyed, but the user still has a handle on this object, and they can use it. So we had to find a way to fix this, and the solution in the end was actually fairly straightforward. Required some changes to our batching algorithm and to our queue implementation. But essentially what we did is we distinguished between MUX command buffers coming from OpenCL command buffer objects and MUX command buffers coming from enqueuing regular commands to the queue and the batching algorithm. So a user command buffer is a MUX command buffer that's come from an OpenCL command buffer object. And this is essentially a flag that we attach to the pending dispatches, and we say this can't be appended to, and it can't be reset or destroyed by the queue, and it may outlive the queue, for example. And this solved our problem. So now you can see in that list of pending dispatches, the read's gone into its own MUX command buffer. The second issue I wanted to talk to you about today is simultaneous use. And Ewan mentioned this earlier, but to recap, this is essentially when you have more than one instance of a command buffer in flight at a given time. So to take an example, in OpenCL, this would be equivalent to enqueuing your command buffer to the command queue and then enqueuing it a second time before the first instance of that command buffer had finished executing. So MUX command buffers don't support simultaneous use. There's nothing in the MUX spec that says they have to support simultaneous use, and it would be absolutely fine for someone implementing MUX to implement MUX command buffers in such a way that they didn't support simultaneous use. However, in our OpenCL command queue implementation, we actually hadn't ever had to consider this scenario before. The thing that was creating MUX command buffers was the queue, and according to that batching algorithm we saw earlier, there's just no way you can get more than one instance of a MUX command buffer in your list of pending dispatches at a time. That was until the SYCLcr command buffer extension. So the command queue implementation we have essentially assumed that MUX command buffers didn't support simultaneous use, and based on that assumption we did certain things, one of which was to associate certain resources to MUX command buffers, like semaphores, for example, those MUX semaphores we saw earlier. And we were doing things like storing those in a data structure, such as a map, and using the address of a MUX command buffer to look up that resource. So in the list of pending dispatches on this slide, you can see that we've added a second instance of the MUX command buffer A. And when we've gone to create some semaphores for that second instance and store those, we've inadvertently clobbered the semaphores associated with the first instance of that command buffer. And of course, both those objects need their own semaphores since we want both of them to execute. So we had to find a way to work around this. And the solution to this was kind of twofold. The first thing we did was make simultaneous use optional. So vendors don't actually need to support simultaneous use for OpenCL command buffers. And you can query support for simultaneous use via this, this flag, which is a property of the OpenCL device that can be queried by the OpenCL API. And if a vendor that doesn't support simultaneous use was had a user who was trying to enqueue a command buffer and it was already in flight, they could, for example, report an error and say this, we don't support this. We have actually worked around this in Compute Aorta, and we do support simultaneous use for targets, for MUX targets that want to. And the way we do this is via the MUX clone command buffer entry point. And this does exactly what you'd expect. You pass it a command buffer and it gives you a new command buffer that's got exactly the same commands in it. It's identical, but it's its own object. And so MUX targets that implement this entry point can support simultaneous use. And the way this works is that when a user MUX command buffer is added to the list of pending dispatches, the command queue checks whether there's already an instance of that command buffer in the list of pending dispatches. And if there is, it makes a clone of the MUX command buffer and adds that to the list of pending dispatches. So you can see in this example that C is a clone of A, and since C is a unique object, we no longer have this issue of clobbering the resources associated with A. And I should point out here that since the queue is the thing responsible for cloning command buffers, the queue is also responsible for destroying the cloned, or the command buffer that's the result of the clone. And this entire process is completely transparent to the OpenCL programmer. So there's no concept of cloning command buffers in OpenCL at the moment. This is just a way to work around the fact that a MUX command buffer object may not actually support simultaneous use, and B, our command queue implementation currently assumes that Mux command buffers don't support simultaneous use. So the final issue I wanted to run through today quickly was printf. So we hit a bug with printf and command buffers and simultaneous use. And the reason for this was to do with how we actually implement the printf built-in. So our printf built-in doesn't actually print anything. When printf is, when there's an instance of the printf built-in inside a kernel, what happens is an implicit buffer gets added to that kernel, and the printf built-in writes into that buffer. And then when that kernel is added to a mux command buffer, there's an associated implicit callback that executes after the kernel, and that callback reads from that printf buffer and then uses the host printf to print the result. So with simultaneous use, we were getting situations like the one you can see on the slide, where there's two instances of a command buffer. They both contain kernels calling printf, and both those printf built-ins are writing into the same buffer at the same offset. So they overwrite one another, and then when it comes to reading that data from those callbacks, you get some garbage or the values you don't expect. So the solution to this again is twofold. The first thing we did was make printf optional inside kernels and command buffers. So similarly to how we did it for simultaneous use, a vendor doesn't actually have to support printf in kernels in command buffers. We do support printf in Compute IWOCL inside of kernels and command buffers with simultaneous use, and the fix for this was to add some offsetting machinery kernel side so that each instance of the command buffer ends up writing into this printf buffer at some offset, and then the callbacks do a similar thing and have some offset that they read at. So each printf has its own region within the buffer, and there's no longer any overwriting. So that was all I had to cover today in terms of implementing the OpenCL command buffer extension and some of the issues we hit along the way. In terms of next steps within the Kronos OpenCL working group, we're looking at releasing some of those layered extensions that Ewan mentioned earlier, and then moving from a provisional spec to a fully ratified one for the base command buffer extension in OpenCL. At CodePlay, we're looking at prototyping some SYCL functionality on top of the OpenCL command buffer extension, and then implementing those same layered extensions. Finally, if you have any feedback about the OpenCL command buffer extension spec, we'd really love to hear it. Any feedback would be massively appreciated. And you can provide that via the link on the slide, which is to the issues page on the OpenCL docs GitHub repo. And yeah, feedback would be really, really appreciated. Finally, I would like to say a massive thank you to everyone who's worked on the OpenCL command buffer spec. As Ewan mentioned earlier, this wasn't just an effort on CodePlay's part. There were lots of members of the OpenCL working group who worked on this, so thank you very much. And thank you for attending this talk. I hope you've learned something about OpenCL command buffers. I hope that if you're a vendor, you're excited to go away and implement OpenCL command buffers, or if you're an OpenCL programmer, you're excited to go away and use them. And yeah, I hope you enjoy the rest of IWOCL 2022. Thank you very much for attending this talk. And me and Ewan are going to be available on Slack to answer questions. Thank you very much.